Hello and welcome to the third part of our lithium battery section. In this video we'll deal more with the separators. Electrodes are electrically separated by a separator that must at the same time allow ions to flow freely. Microporous plastic foils made of polyolefins such as polyethylene or polypropylene or in the multi-layer structure are suitable materials. When a polymer electrolyte is used, polymer can also be used as a separator. Plastic foils are typically 20 to 30 micrometers in thickness with a porosity of around 40%. At cell temperatures above 130 to 150 degrees, PE and PP soften, sealing the pores of the separator. This in turn interrupts the flow of ions. This mechanism is termed shutdown. If a small local short circuit occurs, for example due to a foreign particle, or the cell temperature rises to about 130 degrees, this shutdown function may prevent the cell from being charged or discharged again. If the temperature rises even above 150 degrees, then the separator melts entirely and contracts, removing the electric insulation between the positive and negative electrodes. The separator thickness, porosity, form stability, rigidity can be varied to achieve various cell characteristics. A thinner separator can have an advantage of increasing the cell's energy density. A certain minimal thickness is required to prevent dendrite formation on the positive electrode when there is a metallic separation at the negative electrode, for example during overcharging. Other requirements such as chemical resistance and reasonable manufacturing costs must also be taken into account. Newer separators are frequently made with meshes and membranes or produced with a ceramic coating. These materials are form stable over a wide temperature range, so there is no shutdown mechanism. Then we also need collectors to collect the currents from the active materials. And they require an adequate mechanical rigidity, good wettability, good adhesion to the electrode materials, adequate chemical and electrochemical stability, ideally between 0 and 5 volts, good electrical conductivity, and moderate material and manufacturing costs. Alloying between the electrode and collector materials cannot be permitted. So normally aluminium is used on the positive electrode side and copper on the negative electrode side. The collectors are designed as foils with a thickness of 10 to 30 micrometers. The electrode potentials and possible onset of corrosion must be taken into account when considering the electrochemical stability of collector materials placed in contact with the electrolyte. Corrosive conducting salts may dissolve aluminium, and at higher potentials local pitting corrosion may occur. Pitting corrosion results in cell damage. Aluminium is thermodynamically unstable and its oxidation potential is 1.39 volt versus lithium. So aluminium only gains stability by forming a natural passivation layer during cell operation. Depending on the conducting salt used and the electrolyte potential applied, the electrolyte can be decomposed during the first charging-discharging cycle when the electrolyte comes into contact with the aluminium collector. Since the decomposition causes a passivation layer to form that completely covers the aluminium surface, stable operation of the cell is maintained. This process prevents deep corrosion. If copper is used as an electricity collector for the negative electrode, the copper oxidizes and dissolves at very low cell voltages, even below 1 volt. This is because the potentials at a negative electrode during deep discharge of the cell may exceed the redox potential of copper. As a result, copper ions enter the solution, and when the cell is charged again, copper is deposited on the negative electrode. This reduces the electrode's permeability to lithium ions, meaning a part of the original electrode material is no longer electrochemically active. As the cell continues to operate, this leads to increased lithium metal separation with dendrite formation, risk of short circuit and loss of capacity. And in the next video, we will go and look how the currents are being transported in lithium ion cells. Thank you very much.